All right, welcome all to the IFML seminar. We are very happy to have Professor Varun Jog from the University of Cambridge. He received his PhD from Berkeley and was at Wisconsin for several years after that. And now he's a professor of information theory and statistics in math at Cambridge. So very happy to have you.
All right. So I kind of might have changed the title of my talk a little bit, but hopefully it's easy. Feel free to interrupt if you have any questions during the talk. Happy to stop and answer. Okay, so my talk is about simple binary hypothesis testing. This is probably something that you've seen in your first level, maybe undergraduate or graduate course on probability. The problem is straightforward. You have two hypotheses. Theta is either 0 or 1. And depending on the hypothesis, you observe n IID samples. So you observe x1, x2, xn, and all these samples come from the same distribution. So they come from p to the n, like a product distribution of p when theta is 0, or they come from a product distribution of q when theta is equal to 1. You have n samples, you have to decide whether they are coming from p or q. Okay, so the simplest hypothesis testing setup that you can think of. Your goal is to look at your n samples and declare a theta hat. So theta hat is your estimate, P or Q, and typically you try to minimize the, do it to minimize the error. And in this case, let me focus on the base version of the problem where theta, where the hypothesis itself is drawn from a Bernoulli distribution. So with probabilities alpha and 1 minus alpha, which means that my error probability is going to be alpha times the type 1 error, which means I declare 1 when it is actually 0, and alpha bar, which is the same as 1 minus alpha, times I declare 0 when it is 1. So my goal in hypothesis testing is to minimize this error using the best possible theta hat. Okay. So what do we know about this problem? As you can imagine, given how simple the statement is, the problem has been studied for a long time, and for at least 100 years. And we know a lot about this problem. So one thing we know is that threshold tests are the best. So by threshold, I mean that you calculate the likelihood ratio, P of x1, x2, xn over Q of x1, x2, xn, and compare it to some threshold and declare P if it is above the threshold, Q if it is below the threshold. For the base formulation that I had on the previous slide, the map rule is the best. So map rule means the threshold is the ratio of the prior, so 1 minus alpha over alpha. So compare P over Q to 1 minus alpha over alpha, declare P if it's above that, Q if it's below that. If you are looking at type 1, type 2 trade-offs, so you want to trade off your type 1 error with type 2, then Neyman-Pearson test is optimal. So you have to just figure out what is the correct threshold, and that gives you the type 1 error of alpha, and that will have the minimum type 2 error. Okay, so we know all these things. We also know that if you care about the problem in the asymptotic regime, so what do I mean by asymptotic? I mean that n is tending to infinity, and you care about how my error is going to decay. So naturally, as you get more samples, you have more information, so error is going to decay to 0. Well, question is how fast does it decay to 0? If you care about base error, then base error decays exponentially fast, and even the exponent is known. So it decays like e to the minus n times the Chernoff information between P and Q. So Chernoff information is some notion of closeness between P and Q. So if P and Q are very close, then Chernoff information is big, it's small, which means that the decay of error is slower. Okay, so we know asymptotically how fast base error decays. There are also versions of this in the Neyman-Pearson sort of setting where you fix one type of error and ask how fast is the other one decaying. So here I'm in the second bullet point, I'm looking at sum of both the errors, but if I just care about one type of error by the other is controlled, even that is known that these things decay like exponents that are characterized by some information theoretic quantities like KL divergence. If you fix one type and look at the rate of decay of the other type, you can also look at versions of the problem where both types of errors are allowed to decay and what are all possible pairs of exponents that you can attain, and even that is completely known. Somewhat recent compared to the history of the problem is, I guess you can do what are called second order analyses of the error. So these types of analyses were done in the 1960s, and they also showed up in this work, a very famous work in 2010, which looked at finite block length information theory. And essentially, instead of just looking at the exponent of e to the minus n, like what is the other term after that? What is that little o of one term? And these papers try to characterize those terms. So that type of analysis is also done. So the question is, well, what's left? It seems like Many questions about this problem are already answered. And what's left, surprisingly, was the question of sample complexities, which is going to be the focus of this talk. Okay, so sample complexity means sample size basically. How many samples are needed to get an error of delta? Okay, so you know everything about the problem. You know P, you know Q, you know alpha, and you have some specified delta, and you just are asking what delta, what n do I need to get an error of delta? Yes, question?
Dumb question, maybe. If you know the log deviations exponent, then what is there to be done? Just turn it around, right?
Sure. You will get a value of n that is good enough, in the sense that that value of n will suffice. But the little o of one term.
Bahadur Rao typing and correct it, isn't it?
Okay. So when I say I haven't exactly posed, so I don't want to get a sample complexity as something that is tight in the limit or anything. I want to get a sample complexity that is correct up to universal multiplicative constants. So for any PQ alpha, I want to get a number that is tight up to constants.
Wait, sorry, just to even ask a dumber question, but like, yeah, is what he's saying, like, you have something in terms of n, take that quantity, make it less than or equal to delta, and solve for n.
Yes.
And that doesn't work?
It doesn't give you tight bounds for n. Because there is a little o of one term there. So your error is decaying like e to the minus n times churn of information plus that little o of one term. Depending on what that little o of one term is, your bounds will.
Or equal to Adam, it's just a less than or equal to, it's not equal to.
You said that people had been studying the little one terms in 2010.
That's what
Again, you can. All right. So in the finite regime where you have finite n and you're trying to analyze, there are some drawbacks. So the way these analyses work is you fix one type of error. Let's say if you fix type 1 error to be some constant, and then you see how is my type 2 error decaying. In the type 2 error decaying, you get some extra term, and after that you'll still get some little o terms, and inverting those bounds is hard. So I can tell you that if you take these many samples, then my type 2 error will be smaller than something. But if I want to invert those bounds, saying I want my type 2 error less than that, can you invert this bound somehow and get an n? That is hard, and even if you computationally were able to do that, there are no guarantees on how good that is. Like this value works, but is it going to be up to a constant of 2 tight, or is it going to be dependent on my P and Q, like the accuracy? Yeah, so it's this specific question, which is just a sample complexity question, which is pretty common in like theoretical machine learning. You want to get finite sample bounds on learning problems. That was sort of left unanswered. Okay.
When you say you know P and Q, you know the densities?
Let's just say it's a discrete setting. So some finite support size. Yeah, you know them exactly. You know P of I and Q of I for every I. Yeah. So, yeah. Any other questions? All right. All right. So the talk will have two parts. One will be the classical problem that I just described, and then the second part will be a bit more modern compared to the earlier one version of this problem, which will be about distributed hypothesis testing. And okay, so let me start with the first one, the sample complexity of simple binary hypothesis testing, the problem that I just mentioned. So that's the problem. You have theta coming from alpha 1 minus alpha. You want to get a Bayes error of less than delta, and we call this quantity the Bayesian sample complexity. And it's a quantity that depends on all the things that you have, P, Q, alpha, and delta. All right. And our goal here is to identify the sample complexity n star up to universal multiplicative constants, which means that I want to find some function f, so that when that f takes in these parameters P, Q, alpha, delta, it's going to come up with a number, and the number of samples that I need is going to be close to that, like maybe 1 over 100 that, or 100, some constant times that. And those constants do not depend on any of my parameters, P, Q, alpha, delta. Okay, and just a note that this is not trivial to do algorithmically as well. So let's say you had infinite computational power, then here's what you could do. You know the optimal test already. The optimal test is the map rules. You try n equal to 1. Is your error less than delta? No. They try n equal to 2. Is your error less than delta? No. Keep going on until you reach an n where your error eventually becomes less than delta, and output that. But if you look at the form of the optimal test is a map rule. So for any particular n, I have to find what are all those xn's, so that P of xn over Q of xn is greater than 1 minus alpha over alpha. And that set can be some, I mean, that set does not have a neat description. It's described in this particular fashion, but that set is, I don't know, it's some set of k to the n if k is your alphabet size. So finding that set, it does not seem to be something obvious, something that you can find easily. And then essentially I'm saying that for large values of n, evaluating the error probability is not that easy either. So algorithmically, if you want to solve this algorithmically, it's not that easy. And even if you do come up with a value of n, you don't really have a good understanding of how that n is related to PQ alpha delta. Okay, so that's kind of one comment. So here are some folklore facts. As I said, the problem has been studied for a long time, but the prior work has always been for the uniform prior case. So alpha is 0.5, which means both priors are uniformly likely. And delta, for now, let's say delta is some constant. So that means that you want your base error to be less than some constant, which is say 0.1. Here, we need like one basic fact here, which is that the base error is characterized by the total variation distance between two distributions. So if you have P and Q and you use the optimal map rule when the prior is uniform, then the error probability that you get is half of 1 minus the distance between PQ. Intuitively, this makes sense. If the distance between P and Q is big, the problem is easier to solve. So 1 minus DTV is small, so error is small. If DTV is very small, that means the problem is hard to solve because P and Q look very similar, and so your error is big. Okay, so that's the formula that we need, and you can use some standard results to show that this sample complexity that we are worried about is captured by DTV in terms of lower and upper bound. So it is lower bounded by 1 over DTV up to constants, and upper bounded by 1 over DTV square. And the problem, of course, with these bounds is that they are not tied up to constants, because they can be different by a factor of 1 over DTV, which can be arbitrarily big. Okay, how do you prove these bounds? Okay, so what does it mean to say that I want to get an error of 0.1? It means I want half of 1 minus DTV to be less than 0.1, which means I want my DTV to be bigger than 0.8. Okay. So if I want DTV to be bigger than 0.8, then so 0.8 must be less than DTV between the product distributions, but then data processing gives you that this is less than n times DTV. So that gives you a simple bound that n must be greater than 0.8 over DTV. 0.8 over DTV is like 1 over DTV, so up to constants. For the upper bound, you use a fairly simple test called the Sheffey's test. So here you identify the set A where P dominates Q. So A is a set of all I, so that Pi is greater than Qi. And you reduce the problem to a binary problem. So you say Yi is indicator that Xi lies in A. So you can ask if the true distribution is P, then what's the probability of Yi? It's going to be P of A. If the true distribution is Q, it's going to be Q of A. So if you look at the average, the number of points that happen to lie in this set Yi, that has different means, and using Hoeffding's inequality, so these are P of A and Q of A, and they're separated by DTV. So using a simple Hoeffding bound, you can show that if you take n equal to 1 over DTV square samples, your error will be smaller than a constant. Okay, so that's kind of folklore. DTV gives you some bounds on the sample complexity, but not tied up to constants. So what is the correct notion here? Turns out the correct notion of distance is not total variation, but Hellinger distance or Hellinger divergence. So Hellinger divergence, this is the square of the Hellinger distance, but it's defined like this. It's the L2 norm square between the square root of the distribution. So root pi minus root of p of x minus root of q of x whole square. You can also expand this whole thing out and see that it is basically the term on the right, where this the bracket term indicates I'm doing a dot product of the square root p and the square root q vectors. Okay, so this is some notion of, again, separation between p and q, and it's not hard to show that Hellinger is between TV square and TV up to constants. And the nice thing about Hellinger that TV does not have is this property called tensorization. So what does tensorization mean? Tensorization is this vague word that we use all the time to say that there is some property that you care about product distributions that can be easily evaluated or bounded using a single sample version of that. So here, let's say you're trying to calculate the Hellinger divergence between a product of P's and a product of Q that has a closed form formula in terms of the Hellingers between the Pi's and the Q's themselves. Okay, and this is not a property that holds for TV. If you look at TV between product of P's and product of Q's. That is upper bounded and lower bounded by something in terms of dTV between Pi, Qi, but there is no formula like this. Another function that satisfies such nice properties is KL divergence. So KL between products is the sum of the KL between say individual. So there are these nice kind of quantities that tensorize, and these are always the kinds of quantities that help us for proving lower bounds in a kind of statistical problems, because that seems to be the best way to deal with more samples. You come up with a quantity and you say that I can deal with this quantity because I can deal with the single sample version. Okay. So anyway, so Hellinger is a good notion of distance because it tensorizes. And it turns out that Hellinger is the right quantity that characterizes a sample complexity in the uniform prior case. So when alpha is 1/2, it turns out that the sample complexity, which I said is between 1/TV and 1/TV square, is in fact this quantity, 1/Hellinger square. Okay.
Is this also historically known, or this is something?
This is also historically known, yeah. And I guess I can very briefly sketch the bound. So if you want an error of smaller than 0.1, then you want your dTV to be greater than 0.8, which means dTV square should be greater than 0.8 square. Then use some bound on dTV square using Hellinger. Use the tensorization property quite crucially here. So the Hellinger between products can be written in this form, and alpha here is half of Hellinger square. So you get this inequality, and then you get an n is greater than 0.8 square over alpha. So it's some constant over Hellinger square. To get an upper bound, again use a similar calculation, that if you take if you want to make dTV square greater than dTV greater than 0.8. So use these inequalities, first bound TV by Hellinger, plug in the tensorization formula for Hellinger, and say that this is always greater than 1 minus e to the minus n alpha. So if you take n big enough, then your dTV will be big and you're done. Okay, so fairly simple proofs, just using the fact that TV and Hellinger are kind of well controlled. Okay. Okay, so what was left was what happens for other values of alpha and delta. So it turns out when alpha is 1/2 and delta is not 0.1, but let's say delta is any small delta, then the only thing that changes is the 1 by Hellinger square becomes log 1 by delta over Hellinger square. And okay, so this part works out, and for other values of delta, so the question that remained open for a while was what happens for other values of delta, and why might you care about other values of delta, of alpha and delta? Turns out that when you change alpha and delta, that's kind of saying that the relative weights that you're putting, or when you change alpha from uniform to non-uniform, that means your type 1 and type 2 errors are weighed differently. So for example, you can imagine a scenario where your type 1 error is less than a constant, but your type 2 error has to be very small. Like this one is 0.1, but the other one is extremely small and is equal to delta, which is kind of the setting that happens in the Stein regime. You fix one type of error to be something and ask how fast the other type of error decays. Those kinds of situations are not captured when you have a uniform prior. Uniform prior weighs both the errors equally, and it doesn't say that I want one type of error very small, other type of error is okay. So we don't have bounds for that, and that's what can be looked at. So we looked at this problem last year in this paper, and we found a formula for the sample complexity for all delta between 0 to alpha by 4. So recall that delta is the error. So the error has to be less than alpha. Alpha here is always less than 1/2, and because I can look at 0 samples and simply declare the more likely hypothesis and get an error of alpha. So the problem only makes sense when delta is less than alpha. It turns out the techniques that we have don't go all the way up to alpha, but they go up to alpha by 4, some fraction of alpha. And so we do have a formula, but there are some drawbacks of this formula that I would try to address in this talk. One is that the proof is actually a patchwork of 3 different proofs. So what we did was we had to find a formula that works in all regimes, but we couldn't find one formula. So when delta was sort of linear, a constant fraction of alpha, we used some technical F divergence inequality between Hellinger divergences and Jensen-Shannon divergences to get the bound. When delta is not linear but between polynomials, so between alpha by square to alpha by 100, there was a sort of a boosting argument, which means you you take multiple batches of your data set and declare the majority decision on each of the batches. And the last thing was when delta was very small, it's sort of like you're in the asymptotic regime. So this is where the exponential e to the minus Chernoff information type results start kicking in. So when delta is really small, the results that you get from the asymptotic analysis agree with finite sample analysis. So we have 3 different regimes and 3 different proof arguments and 3 different formulae basically. So in each regime we had some formula, and these formulae look very, very different. And I'm not writing the formula here, but the kind of main drawbacks of that result was that it was hard to parse. It was hard to understand what exactly is the thing that is determining the sample complexity. The constants involved are very large. So as I said, like we want to find sample complexity up to universal constants. The constants there were about 200. And thirdly, this is what kind of bothered me the most, is that the proof was very fragile. So which means that if you have independent samples but non-identical samples, then the proof breaks down. And these kind of situations arise very naturally in distributed hypothesis testing. So under a hypothesis P, you get n samples, but P1 times P2 times Pn, and under Q, you get Q1 times Q2 times Qn. And this proof technique that we had could not handle that. Okay, so that's what we are trying to address here. So I'll try to explain how you can get a better proof and a better formula using what are called one-shot bounds. Okay, so here's again going back to the basics. Let's say we just have one sample, exactly one sample, and we calculate what is the base error that you get for the optimal map rule. It has a simple formula, like the error E alpha, which is the base error, has this formula. It's a minimum between alpha times pi and alpha bar, which is 1 minus alpha times qr. So that's a formula. Yes.
I have a question, maybe a little bit of a tangent, but suppose, is this even meaningful? Suppose I have a series of random variable xi under some measure p, and I have a test variable for testing some property of it.
Okay.
Like this is an example. Now I say I change the measure on xi to p, and I give you the Redon-Nikodym derivative. I give you dq by dp. Then is there a clean way of just using the previous test and this dq by dp to give you a new guarantee? Because the kind of question you're asking is essentially this: I can just twist the measure on theta, the base, and look at 2 different. Maybe it's a side. Forget the connection to this. Is that?
I didn't get the question. Can you explain?
I give you a IID random variable with a measure p.
Yeah.
And I give you a test which is a function of this p, and gives you maybe a threshold test or something like that, and gives you a performance statistic. Say n star. In this case, you need to spit out n star. Now I say the measure is going to change from p to q, and I'll give you the Redon-Nikodym.
Okay.
How is the measure going to twist? Is there a large deviations way of twisting, going through this test and giving you a new guarantee all the way to the other end by some exponential tilting?
I see. Right, so instead of, you're trying to find a path from P comma Q to Q comma Q somehow.
Yeah.
And
is this kind of, it's not well formulated what I'm asking, but is this style of things done?
there is, okay, I'm not sure. So some tilted type measures are going to show up, but not really in the sense of, they show up just because I'm using some AMGM type inequalities. I'm not deliberately going to consider a path of distributions like that shows up in large deviations. Yeah, there is that path P to the lambda, and yeah.
I'm seeing whether what you think can be thought of as a new path problem.
I see.
That's what I'm trying to do.
I'll try to think about it. Okay. All right. So here's the formula if you have just one sample, and I'll tell you how to get some nice upper bound. So minimum between two quantities is always less than any average that you take between them, right? It's less than the arithmetic mean, geometric mean, whatever. So all I'm doing is that I'm taking minimum of alpha pi and alpha bar qi and upper bounding it by the geometric mean, but not with 1/2 that we usually do, but with some lambda. Okay, and I get this upper bound, that error is always upper bounded by this quantity. Let me call the quantity in blue this beta lambda, which is called the affinity, the Hellinger lambda affinity between P and Q. Why do we like this beta lambda quantity? The moment you have product distributions p to the n and q to the n, so E alpha of p to the n q to the n is going to be upper bounded by the same formula, but now you'll have beta lambda between p to the n q to the n, and this beta quantity tensorizes. So beta lambda between p and qn is beta lambda pq to the power n. Okay, it's a simple exercise to check that this nice summation in blue, the moment you have product distributions, is going to become a power of what it was. So that's a fantastic property for this beta lambda. So whenever you have tensorization, it's great for proving upper bounds, because you say that I want my E alpha to be smaller than delta. So what do? I just find a value of n here, so that when I raise it to the power n, my right hand side becomes less than delta, because that isn't a valid upper bound on E alpha, and I'll get
Beta lambda again,
so beta lambda is exactly this term in blue. It's sum over all I, pi to the lambda, qi to the 1 minus lambda. Yeah. So getting an upper bound is fairly straightforward. In fact, you get an upper bound on every choice of lambda. Plug in whichever lambda you want. You get find out the beta lambda, and just find out what is the value of n that I need to make this quantity with beta lambda to the power n smaller than delta. That gives you an upper bound. And this is pretty much this is a very simple upper bound, and it works. Like if you adjust your lambda suitably, it's going to give you good tight upper bounds. The difficulty is often in proving the lower bounds, and the reason why our previous paper had these 3 different regimes and 3 different formulae is that the upper bounding technique remains the same in all of them, but getting a lower bound involves. Okay, so the standard technique that you might have seen in information theory type class is Fano's inequality. You can use Fano's inequality and get a lower bound, but that lower bound only works in one regime. So you prove tightness in that one regime, then you move to the other regime and say, okay, I can't use Fano, I have to use something else. So you devise some different technique to reduce it to a regime where Fano eventually works, and then that gives you a second formula. And for the final regime where the error is very small, you have some other technique which relies on the bounds between Hellinger and TV, and that gives you. So the reason why there were 3 different bounds is because we couldn't really come up with a good lower bounding proof that works in all 3 of them. We just to come up with a different technique in all 3 bounds. Okay, so what we discovered earlier this year was that there might be a better way to think about this, which is to try to get a lower bound that also tensorizes. So upper bound, as I said, has this beta lambda term, which is very nice, and it tensorizes. Wouldn't it be nice if you could get a lower bound that also tensorizes? And this is the bound that we have, that there is some lambda star. So the upper bound works for every possible lambda star. The lower bound is like, take this particular lambda star, which is some number between, which is some function of alpha and delta. And this error probability is lower bounded by something that depends on the Hellinger affinity at that lambda star. Okay. I mean, on the face of it, this result seems kind of useless, right? Like, typically, if you're trying to lower bound something, you better not know that quantity already, right? So, but the way this is written is that if I want to get a lower bound on the error, to calculate my lower bound, I already need to know what the error is, right? So, in that sense, it seems a kind of a useless bound. But the way to think about this is, it starts becoming useful when you look at the product distributions. You say that I'm going to take n samples, and when I take n samples, my error becomes delta, which is something small. So when you take n samples, then you can plug in delta is therefore greater than something, beta lambda star p and qn, and then you can use tensorization and get some bounds on n. Okay. So that's where kind of the niceness of this quantity comes, and the other nice thing is there are no regimes here. It's something that works. It's just an inequality for E alpha. So you can plug it in and get lower bounds in every possible regime of delta. Okay. Yeah. This is just to compare it with the upper bound. The upper bound is something of this sort. As I said, the upper bound works for every choice of lambda. So in particular, it also works for this choice of lambda that we have picked. So the upper bound is in terms of beta lambda star, lower bound is beta lambda star squared. The square doesn't really matter in terms of the sample complexity, because eventually we are going to take logarithms and it just becomes 2 times something and log of beta. Okay. Okay. The proof technique is, it sort of uses these information theory tricks that if you want to prove a result for all P and Q and it seems hard to prove, reduce it to Bernoulli. So say that it's enough to prove this theorem just for Bernoulli P and Q, which means just each P and Q are supported on just 2 points. And if you can prove it for Bernoulli P and Q, then it holds for all P and Q. This is kind of a standard argument that we use to prove, let's say, Pensker's inequality. So if you want to bound total variation by KL divergence, you say that I'm going to prove it for Bernoulli and then use data processing to show that it works in general as well. Similar kind of ideas work here. So reduce it to Bernoulli, but after you reduce it to Bernoulli, it still becomes a bit ugly. So you look at the set of all Bernoullis where the left hand side is fixed, the E alpha is fixed to be delta, and try to find, well, how big can my right hand side be? But unfortunately, this right hand side, for every choice of lambda, is some weird concave function, and you can't really optimize it very well unless you choose your lambda nicely. So optimizing a concave function is, in general, it's hard because you have to find where the derivative becomes 0 and everything. But if you choose a lambda nicely, then that concave function turns out to be, you can make it basically constant. And then you can say that the maximum of the concave function is the value of the endpoint, so that is easy to evaluate. So this choice of lambda star comes in that evaluation. I want to somehow evaluate this maximum in some nice way, so I just choose a lambda star nicely. Okay. Okay. So eventually, once you go through the calculations, you get this formula that the sample complexity, it's now a formula that works in all regimes. There are no 3 different formula or anything. It's captured between some quantity, half of some quantity, and twice of some quantity. And now it's kind of clear like where, why there were 3 different. I mean, this formula can recover all the 3 different regimes, but it shows that really what's happening is you're just calculating the affinity at different lambda stars based on alpha and delta, and it's just that we didn't recognize this is what was happening in the previous paper, and that's why we got 3 different regimes with 3 different formulas, but this reduces to the same formulas in those regimes. The second point is the constants are really good here. The constants earlier were like 200 or something. Here the constants are just half and 2, and in fact they can be made arbitrarily close to 1, which means, so right now I'm saying delta is between 0 to alpha by 16, but if I say delta is between 0 to alpha by 100, then the constants, both constants tend to 1 as my, so essentially these constants could be replaced by something as a function of delta that goes to 1 on both sides as delta becomes small. So that's nice, and lastly the proof technique is more robust, so this is going to be useful in the distributed setting that we were studying. Okay, good. All right, so pivot now. So what is the distributed hypothesis testing problem? This is also a fairly old problem, so not as old as a simple binary hypothesis testing, which is like 100 years old, but this is, I would say this was studied very well, studied quite a lot in the 1980s, and this is a survey paper by John Tsitsiklis in 1989. So back then they called decentralized detection, and the motivation was sort of sensor network. So you have a bunch of sensors that are connected in some sort of a network. Each sensor observes some xi, and the sensors are talking to each other, maybe funneling information to some central server, and the central server has to figure out what's going on looking at the sensor data. So maybe the hypothesis testing problem would be each sensor is receiving xi from P or Q, and the central server has to determine whether it's P or Q, whether the hypothesis is P or Q. But because of the network form and because of some constraints that the sensors might have, the central server doesn't receive all the information but gets some warbled information, and they still have to decide what it is. Okay, so the sort of canonical example is this one, where you have n sensors, like n sensors, and one fusion center is what they called it in the 80s. So each sensor is receiving one sample. So x1, x2, xn are still IID, all coming from P or all coming from Q. But instead of the fusion center having access to these original xis, they only see some version of xis that the sensor is choosing to share with them. So the common kinds of constraints that we have in these settings is that each sensor might be quantizing things. So let's say the observation is on a very large alphabet, but the yi has to be 1 bit. So you can only send 0 or 1. So each of these yi's are only 0s or 1s, and you have to figure out what it is. You might also think of privacy. So each sensor could be trying to protect its data in an epsilon delta privacy fashion. So what they do is they don't send yi equal to xi, but they send yi to be some noisy version of xi, so that sort of protects their value. So I'll focus on the quantization version here. So each each user or each sensor has to quantize xi to d levels or log d bits. And clearly this is a harder problem to solve than the original one, the centralized one. So you're going to need more samples to solve it now. Because every time you quantize, you destroy information. So to get the same amount of information to solve the problem, you need more n. So the question is how much more n would you need? And the problem, well, the answer depends on many things. So one is how are these quantization methods chosen? So are all these sensors coming from the same factory so that they use the same function f to go from xi to yi? Or are they allowed to use their own quantization functions? So maybe f1 for sensor 1, f2 for sensor 2, and so on. Or even more, are they allowed to adaptively choose their quantization function? So the ith sensor can see y1, y2, yi minus 1. They can see what the previous sensors have already transmitted. And then the ith sensor uses their own some clever algorithm to choose a particular quantization function and then sends their own yi. So this is called adaptive. So this is called sequentially adaptive. Fully adaptive is when you have multiple rounds of sequentially adaptive communications. So anyway, all these questions, all these settings make sense, and your final answer could depend on all of these potential formulations. Okay, so what's known for this? So let me call the sample complexities in all these settings as following. N star is the standard setting with no constraints whatsoever. N star identical, ID is when you have identical sensors, so all sensors are coming from the same factory, say. N star non-identical is when they can use different quantization functions, but they are not talking, the sensor cannot see what anyone else is seeing. N star sequential is when they can sequentially see, so the ith sensor can see the previous things, but not the future thing. And N star BB stands for Blackboard protocol. This is like the most general form where you have multiple rounds of sequential conversations and then eventually they stop talking. Okay, so what was known in the past? It was known that using non-identical sensors does not give you much of an advantage. So you might as well use, if you have to choose between identical and potentially non-identical, just fix the same best sensor and use it everywhere. That was known. Again, everything, all prior work for only uniform prior. It was known that if you have a quantization constraint of d, then your sample complexity sort of grows, but does not grow that badly. Like it does not become a square or cube. It grows up to log factors, right? So in CS theory, you would put an O tilde and forget about it, right? Like n star identical is n star log n star over t. Okay? And it also kind of says that what is the d that you need to not suffer any loss? The number of quantization, if your number of quantization levels is log of n star, then you don't suffer any loss at all in using the communication constraint. You can solve the problem with basically the same number of samples. Right, but there are several open problems. One is whether this equality between identical, non-identical holds for all alpha delta. It's something special for alpha equal to 1/2. Whether this inequality, whether identical is less than n star log n star by d, also holds in all regimes. And lastly, kind of more wide open was what is this? What is the benefit of adaptivity? Like, does the sequential adaptivity help you? Does the Blackboard protocol help you? Is it going to bring down the sample complexity significantly or not? Okay, so this is our contributions here are. Well, one of our main results is the following, that sequential adaptivity does not help you. Okay, so which means that if you give your sensors the freedom to sequentially choose, the sample complexity will go down at most by a factor of 4. So if you don't care about constant factors, then n star sequential is the same as n star identical, which is also the same as n star non-identical, because non-identical channels is a subset of sequential. You just decide what you want to do without looking at the previous ones. So that was one new contribution, and here we crucially use the fact that this new proof technique that we had was not dependent on independent identical samples. That's because if each sensor is choosing to talk based on what other sensors have said, the distribution of yi is not going to be IID. It's going to be something else. Now, if everyone is using the same sensor, it would have been IID. But if they're using different sensor, it's not IID, so the previous proof technique sort of broke down. But here everything still works, because whenever we care about error probabilities, we care about this E alpha. We have a formula that says if you want to study E alpha, just study this new quantity beta lambda, which is the affinity. But affinity has very nice properties, it tensorizes. So, and so you can get this result quite in a fairly straightforward manner. Just a comment, this holds beyond quantization. You could have privacy and the same result holds. Okay, so what this result says is that it's now enough to just study n-star identical. So if, let's leave out the blackboard protocol for now. Because all these sample complexities are basically the same, it's enough to analyze what is n-star identical and try to see if n-star identical is n-star log n-star by d in all regimes. And here you can have a very nice sort of data processing perspective. So let's say your quantization function is some channel, right? So you get P and Q, you pass them through some quantization channel, and you get P prime and Q prime. Data processing says that any sort of processing makes things closer. So if P and Q are initially far apart, you pass them through a channel to get P prime, Q prime. Any distance that you care about is going to go down. So if you care about KL divergence, total variation, Hellinger, whatever you care about, it's going to become smaller after the channel. We know that sample complexity is determined by this beta lambda parameter, which is in fact 1 minus a divergence. So 1 minus beta lambda is a Hellinger divergence. So sample complexity is characterized by the lambda Hellinger divergence. So what's happening is you want to make sure that so data processing is telling you that lambda Hellinger divergence is always going to go down, so sample complexity is always going to go up. But you have a choice of what channel to use. So among all possible channels, so your input is of size k, which is your alphabet. The only restriction you have is that the output is of size d, because you're quantizing. So among all these channels, you want to use that one channel, or you want to use that channel which processes the least. So things are coming close, but you want to keep them as far apart as possible. You want to have sort of a reverse data processing inequality, where you're saying that there exists some channel out there which is not destroying information. So the P prime and Q prime keep being far apart even after passing through a channel. And this is sort of a reverse data processing inequality that we showed, that you can prove these kinds of inequalities for a large class of F divergences, including Hellinger, total variation, Hellinger lambda, and many F divergences out there, which is that the output, output distance, so output df, you cannot capture it up to constants. So you have to pay some price. So but the price that you pay is this quantity. So if df is very small, then you can imagine that this d over log 1 by df is a very small quantity. So you are losing a lot of it, but you can preserve the f divergence up to log factors. Okay, so it's saying that yes, you do pay a price. You cannot preserve a constant fraction of the f divergence. You cannot say that the output f divergence is half of the input f divergence, but up to log factors you can preserve it. So you don't have to pay a very high price for preserving f divergence. It also tells you, well, what is the level of quantization at which you don't pay any price. So if the number of quantization levels is log 1 by the original df, then you pay no price. You can exactly, or up to constants, preserve the f divergence. Right. So once you have this reverse data processing inequality, you can immediately conclude that if identical channels is all that you care about. So we already said that sequential is the same as non-identical is the same as identical. So let's just study identical. And in the identical regime, you can see that n star identical is n star log n star by d. So roughly it says that communication constraints or quantization constraints are benign in pretty much all the regimes of alpha delta. It gives you a log factor growth at most. Good. All right. So yeah, I don't have too much time, but I just want to give one result that I'm quite fond of, that this relies on. So the proof relies on something called a reverse Markov inequality. So all of you are probably familiar with Markov's inequality, that if you have a non-negative random variable, then probability that x is greater than some t is upper bounded by expectation of x over t. Okay, so it tells you some basic tail bound on a random variable with finite expectation. This is a reverse Markov inequality. Okay, so if you forget the supremum for now, then probability x greater than t is always less than t t times probability x greater than t is always less than e of x. Okay, so usually this inequality holds in the reverse direction with no log terms and no supremum. I mean, it holds for all t. So what we want here is kind of this is a reverse inequality. It says, well, what if you are allowed to choose that t to maximize this quantity on the left? Well, it turns out you cannot get a constant fraction of e of x, but you can cleverly choose a t so that it's up to log factors, it's fine. So e of x over log 1 over e of x. Okay. This result is for d equals 2, but you can there are versions of this result for higher values of d2. And the proof basically relies on this. So what we do is we just identify a nice random variable so that the right hand side, so that the left hand side is the Hellinger lambda of the quantized version. So t is the thing that is deciding where to quantize, and the right hand side, and each lambda of pq is e of x. So you just have to look at the expressions and see like how this inequality fits into the result that we want, and it just pops out. Okay, so just a quick summary. We have a better approach to proving the sample complexity using these one-shot bounds. This beta lambda parameter is showing up, nice. So it kind of unifies the previous results, improves the constants, and gives us just gives us a better way of analyzing. It gives you a better way of proving lower bounds. So you don't have to. Maybe if Fano is not working out for you in your situation, you might try to use this lower bounding technique. There's a new reverse data processing inequality, and there are some open directions that we haven't figured out. So the first bullet point is, so all our proof techniques fail when delta becomes very close to alpha. So delta is the error. It works when delta is less than alpha by 10 or alpha by 16 or something. But when delta is very close to alpha, we have upper and lower bounds, they don't match up to constants. And this regime is kind of important in statistics. They call this the weak detection regime. So are you doing better than random guessing or not? Like you want to do, if you don't look at any samples, you can get an error of alpha already. So what if you want just less than alpha? How many samples do you need? We don't have tight bounds in that cases. The third bullet point is also kind of an open problem, that does full interaction help? If you have multiple rounds where you're talking, can that actually help? We don't have a lower bound or an upper bound. We don't actually have a guess at all whether it helps or not. So that's kind of wide open. And here's a reference. Hopefully we'll have it up on archive sometime soon. That's it. Thank you.
Thank you.
Yeah.
So you sort of alluded to the fact that these sort of bounds can be applied for differential parameters too.
Mm-hmm.
So can you just give us a hint, like how does this just look like?
Right. So in the distributed hypothesis testing setting, the quantization one was that yi has to be a quantized version of xi. The differential private setting says that yi has to be a private version of xi. So privacy, the definition of privacy means that if you look at the channel transition matrix, then sort of probability of y given x is within an e to the epsilon fraction of probability of y given x prime for any x at x prime. So that restricts the class of channels that you can use to some polytope in the set of all possible channels. So most of the techniques are kind of the same, that it's just that instead of the set of channels being the set of all k by d, k through d channels, you restrict to the set of all private channels. So let's say you have an additional constraint of private channels with also an output constraints. Then it gives you some polytope of the set of all channels, and you can use these ideas to get the results that the sequential interactivity doesn't help, that identical and non-identical channels are basically the same, still hold. What stops working is the actually finding out what is the sample complexity when you use identical channels. And that's because finding the best possible private channel in this polytope is like a very complicated. So algorithmically, actually, we showed it's easy to find. So we can find you, we can give you what the channel is that you should use, but we can't analyze its performance. So that's where we are kind of stuck. We can get upper and lower bounds, but we cannot analyze like how good is that private channel. That may be, I don't know how to fix it, because maybe we are just using the wrong notions of F divergences. Like here, like once you identify the right notion of divergence, somehow things fall into place. in the paper that we wrote, we looked at TV and Hellinger, and those don't seem to be the right notions. So, yes.
What about for null hypothesis testing, where you have a P but Q is something far?
Yeah, I've been thinking about those. So the kinds of problems that it would be good to have bounds for would be like kind of hypothesis testing where it's called identity testing. So either it is exactly coming from P or it's coming from a distribution Q that is more than epsilon away from P. I don't think any of the techniques that we have continue to work there, because this relies quite heavily on the structure of map and the fact that you know P and Q. But yeah, but those are interesting problems that I do think about from time to time. Yes.
And do the lower bounds here apply to identity testing or say private identity testing, because they're generally for L2, L1 based distances, right? There's like a discrepancy between L1 and L2 based identity testing.
Right. So the way I would think of applying these lower bounds is in whichever scenario the lower bound that Lacam's, so Lacam 2-point testing is like you come up with a worst case P and Q, and you get like a probability of error kind of bound for the worst case P and Q, and that gives you a bound. And if that bound is going to be tight, then these results. So if you can reduce the hardness of the problem to a simple hypothesis testing problem, then this technique is going to be tight.
Can you go back to that lower bound remark, reverse Markov question here?
Yes.
So if I put t equal to median, then median times p of x greater than median is just t by 2, is median by 2 on the left hand side.
Right.
So I've already shown the existence of a lower bound which is median by 2.
Yeah.
And so can't I get a mean median inequality somehow and just get a bound also for that one?
Yeah, maybe that could be one way, but okay, so maybe
Within a standard, now we know mean minus median is no more than one standard deviation. So I've gotten a lower bound which is
right.
mean minus standard deviation.
Yeah.
I've constructed a different lower bound. I'm just curious because you're paying a log 1 by ex penalty. I'm wondering whether that's actually, it could be bad. I'm not sure.
Yeah.
Whereas I've got now within one standard deviation. I don't know how that's going to compare to this.
Yeah, I think the difficulty is like I don't have a operational interpretation of the median in this particular context. So because my E of x is coming as some h lambda, but my median, I don't know whether it's related to any it does not have any bearing on the problem that we are dealing. So I have to have some bound that is purely a function of E of x. That's why I get this one.
Thanks.
Thank you.